They say ammonia, they have some property data, and how does it change from a liquid to a vapor at 0 degrees C. So at 0 degrees C, they say the saturation pressure is so many kilopascal, V sub F and V sub G are given, H of Fg is given, S of F and S of G are given. Estimate the saturation pressure at -20. So what is Psat at -20 degrees C, not knowing any measurements at -20, but only the measurements at 0? So what you do is you will find that we'll drive this Clausius-Clapeyron equation, right here it is, and you would use this relationship between properties, how they change with other properties, to infer the saturation pressure from other data. So find it at -20. Okay, well, let's take a look at this equation. We have the derivative with respect to temperature of the natural log of the saturation pressure equal to the change in enthalpy divided by RT squared. Well, let me just say what I'm going to do is this is a derivative with respect to temperature. I'll separate it, so I'll get a derivative of the natural log of P equal to change in H divided by RT squared dt. So I brought that dt over. We'll go ahead and integrate this, where we integrate from the consistent lower limit, both sides of the integral, to the same upper limit, both sides of the integral. The left-hand side is easy. We get that it's the natural log of the saturation pressure at the end. Let's say I'm going to end at -20 minus the natural log of the saturation pressure at the beginning. I start at 0 degrees C. Hopefully that made sense, how we treated the left-hand side. Now let's take a look at the right-hand side. Delta H and R come outside the integral. We just have now the integral of 1 over t squared dt. Professor, it's been a long time since I had to integrate, but this is -1 over t evaluated at those upper and lower limits, true? So what we're going to do is we're going to evaluate this. I'm going to do it this way. I'm going to put it like this. I'm going to get rid of that negative sign in the lower limits up here and the upper limits right there. What was our consistent lower limit? That was at 0 degrees C, and this consistent with the upper limit over here, it was -20 degrees C. Well, I think we're going to need to use Kelvin, so let's go ahead and use Kelvin. So 0 degrees C is 273, and -20 is 253 Kelvin, right? So that's what we have. So what we have is you're going to have a delta H divided by R, 1 over, basically, I'm going to put numeric values in there, minus 1 over 253. All right. So if you want to, the saturation pressure at -20 degrees C is equal to the saturation pressure at 0 degrees C times the exponential of delta H divided by R, 1 over, I guess I shouldn't have put those 273 here. Temperature 0, temperature -20, temperature 0 minus 1 over temperature -20. All right. So if I ran out of room here, but take it up right here. Oh, shifted it. There we go. So now if I substitute values, we'll have the Psat at -20 is equal to the saturation pressure at 0, 429.6 kilopascal, exponential FG was 1261.97 kilojoules per kilogram. The R is R bar divided by the molar mass for ammonia, and the molar mass for ammonia is 17.04 kilograms per kilomole, right? So that's 17.04 kilograms per kilomole. And then 1 over the temperature T naught is 273 minus 1 over 253 Clausius-Clapeyron, and the saturation pressure at -20 comes right at 203 kilopascal. How does it compare to the table value 190 kilopascal? So it's close, but it's not spot on. It's 20 degrees different. So you extrapolated, or you predicted away from the data point 0 degrees C to Psat at -20.